Perpetual motion machine. Chapter 6.5, yeah? It is any device that violates the first and the second law. Okay, so device that violates the first law, which is devices that create energy, is known as PMM1, and device that violates the second law is known as PMM2. Yeah. Despite numerous attempts, no perpetual motion machine is known to have worked. So there are some claims from some scientists saying that they have actually created perpetual motion machine, but actually it does not exist. Yeah. Okay. Now the reversible and the irreversible processes. The reversible process is a process that can be reversed without leaving any trace on the surrounding. So it's a perfect process. Yeah. So irreversible process is processes that cannot be reversible. So these are the common ones that we have in our daily life. Yeah, mostly reversible ones are nice on paper, on theory, but sometimes it just doesn't exist. It's not too easy to actually have reversible process. Yeah. Okay. All the process occurring in nature are irreversible, like what I've just explained. Why are we interested in reversible process? Yeah, so for the textbook purposes, for theoretical understanding, they're easy to analyze. Okay, and they serve as an idealized model and shows the theoretical limit. So we actually study on the irreversible processes to actually know what is the ceiling or the height of the best the best process that we can achieve. So that's the reason why we need to study on the reversible processes. Yeah. Okay. So what are irreversibilities? Irreversibilities are factors that causes a process to be irreversible. Okay. Example, friction. So friction is a good example. I think every one of us know what is friction. And then we have unrestrained expansion of gases. Yeah. And then also you have some heat transfer through a finite temperature difference, electrical resistance, inelastic deformation of solid, chemical reaction. So these are examples, some of the examples of irreversibilities. So irreversibilities are factor that causes the process to be irreversible. Yeah. Okay. The heat transfer through a temperature difference is irreversible. Yeah. The reversible process is impossible. Example, look at this case. Yeah. Look at this case. Heat travels from outside, yeah, which is 20, to the can, which is 5 degrees. But you cannot have heat transfer from the 5 degrees to the 20, right? Yeah. So this is one example of an impossible heat transfer. And this is an irreversible process. Yeah. Okay. So these are the reason why we have to study this chapter. Okay. Okay. They have two. One is internally irreversible and externally irreversible. Yeah. Okay. Now internally irreversible means if there is no irreversibilities occurring within the boundary of the system during the process. You're well aware of the term boundary. So whatever that happens within the boundary is known as internally irreversible, whereas externally irreversible is anything that is above outer than the boundary. Yeah. Okay, so in your body, remember, boundary can be your skin. Yeah. Totally irreversible process involves no irreversibilities within the system or its surrounding. A totally irreversible process involves no heat transfer to the finite temperature difference, no non-quasi-equilibrium changes, and no friction and no dissipative effects. It's kind of like a perfect process. Yeah. Okay. Okay, like example, this one. So this is totally reversible. Okay, and this is, okay, let me see. Yeah, there's no irreversibility inside the system. So if you have this kind of cases, then this will be a total reversible process. It's a perfect process. Whereas the boundary is at 20 also, and this is internally reversible. So within the boundary, if anything that's within the boundary, then we say internally reversible. Whatever that's outside, then it is external. Yeah. Okay, let me just go into Carnot cycle. I'm just introducing to you Carnot cycle. So what is Carnot cycle actually? It is the best known reversible cycle. It means it is a perfect cycle. Yeah. Reversible cycles cannot be achieved in practice because of the irreversibilities. But then this Carnot cycle is to be known as the best reversible cycle. Yeah. So the theoretical heat engine that operates on the Carnot cycle is called the Carnot heat engine. We're going to come to that shortly. So let's look at the process. 1 to 2 will be reversible isothermal. Isothermal means temperature is constant. Expansion, so expanding, that will be process 1 to 2. And then we have process 2 to 3. 2 to 3 is this one. Yeah, that is the second process. This is the first process. So what is 2 to 3? Adiabatic expansion. So what is adiabatic? There's no heat transfer outside. It's a well insulated system. Yeah, no Q. There's no Q transfer. So in this case, the temperature will drop from TH to TL. And then we have isothermal compression. Isothermal compression is this process. Yeah, compression means pressure will increase, and then it's isothermal, temperature is kept constant. Okay, and then we have reversible adiabatic compression. That will be process 4 to 1. Yeah, 4 to 1. Remember, this is a cyclic process. Yeah, so it will be 1 to 2, 2 to 3, 3 to 4, 4 to 1. It just repeats. Yeah, and this is once again adiabatic, and it's undergoing compression process. So the temperature will rise from TL to TH. So this is an example of a reversible process which is known as the Carnot cycle. Yeah, I'm looking at page a textbook page 296. So this whole process 1 to 2, 2 to 3, 3 to 4 and 4 to 1 will be represented by this PV diagram. So this is a PV diagram for Carnot cycle, and this will be for a reverse Carnot cycle. So let's look at the difference. Yeah, so 1 to 2, there is a QH that's going in, and then the pressure is actually dropping. And we have an expansion in the volume. So how to look at it? Can you see this value? 2 is here, so we have 1 here. Okay, and then we have 2 to 3, 2 to 3, and we have further increase in further decrease in pressure, and then the volume is also expanding. And then we have 3 to 4, which is QL heat being released. Yeah, and then we have what we have here is that decrease in volume. It means pressure is increasing, and a sharp increase in pressure from process 4 to 1. This is how it is. Yeah, and all this diagram here is being represented in the graph, whereas this diagram will be the reverse Carnot cycle. Yeah, Carnot heat engine cycle is totally reversible. Yeah, heat engine, Carnot heat engine cycle. Yeah, so therefore all the processes that comprise it can be reserved, and in which case it becomes a Carnot refrigeration cycle. So just now you see 1 to 2, 1 to 2 was this side, right? And this one will be 1 to 2 this side. Okay, and then 2 to 3, 3 to 4 and 4 to 1. The flow is actually in the opposite direction. This flow is this side, whereas this flow is on the opposite direction. Yeah, okay. So next would be the Carnot principle itself. The efficiency of an irreversible heat engine is always less than the efficiency of a reversible. Of course, the reversible is the perfect one. So definitely the efficiency of an irreversible will be lesser than the reversible. The efficiencies of all the reversible heat engines operating between the same reservoir will be the same. Reason being because temperature is actually the factor that is taken into account. I'm going to show that shortly. Yeah, so this diagram here shows the Carnot principle, and this is the proof of the first Carnot principle. Okay, this is the same thing. This is actually showing you see this TH1000, even though you have two different what do you call heat engines. Yeah, totally different, but because they have the same reservoir 1000 to 300, a drop between 1000 to 300, your efficiency will be the same. Okay. Next would be the temperature, thermodynamic temperature scale. Now this chapter 6.9 is actually to prove your temperature scale. It's actually with all the derivations actually heading to this formula here. You can just read up on it. Okay, that's all for this lecture. Thank you.